In this segment, let us look at the solutions for the harmonic oscillator using the quantum mechanical methods and the solution of the Schrodinger equation time independent h psi x is equal to E psi x. The x is the position coordinate for the harmonic oscillator motion, and the wave function is a function associated with the harmonic oscillator, and it has the same probability interpretation as you have with the particle in a one dimensional box, namely psi squared dx represents the probability of finding the harmonic oscillator between x and x plus dx, x and x plus dx. The h is of course the Hamiltonian operator, and the Hamiltonian operator in quantum mechanics is obtained from the classical Hamiltonian, which is p squared by 2m by changing the momentum to the operator and also half k x square, where x is the position operator. And in quantum mechanics, of course, in this case p is to be replaced by the standard representation in coordinate with the derivative minus I h bar d by dx. It is one dimension, so we do not need the partial derivative. It is I h bar d by dx, which leads to immediately this formula, namely h is minus h bar square by 2m d square by dx square, as you had it in the particle in the one dimensional box, with half kx square, which is the potential energy associated with the harmonic oscillator. Therefore, the solution that you have to obtain is the solution that h psi is equal to E psi, sorry, there is no cap on the psi, is equal to E psi is the solution of the differential equation, namely minus h bar square by 2m d square psi by dx square plus half k x square psi minus E psi is equal to 0. So, second order linear differential equation. This lecture will not tell you how to solve this differential equation, but it will tell you that if you rewrite this by introducing a simple parameter, say for example lambda is equal to 2m e by h bar square, and another constant alpha or alpha squared as km by h bar square. If you introduce two new constants, then it is possible for you to write the differential equation as d square psi by dx square plus lambda minus alpha square x square psi is equal to 0. I think verify this will be one of the items for you to check. It is possible to transform this into what is known as the Hermite's differential equation, for which solutions have been known for more than 100 years when this itself was proposed. In fact, the Hermite differential equation, let me write that down. The Hermite differential equation is d square h, the Hermite function dx square minus 2x dh by dx plus lambda by alpha minus 1 h is equal to 0. Now, I have just pulled this out of nowhere, but it does not matter. What is important is the wave functions psi are going to be associated with what are known as the Hermite functions or Hermite polynomials, and will also have a component called the Gaussian, which is e to the minus alpha x square by 2. This Gaussian and the Hermite polynomial x will determine the solutions of the harmonic oscillator. The mathematics is involved, we do not need to worry about it. What I would do is to write down directly the solution of this equation which you have here. This equation, and then we will only examine the nature of the solutions and the consequences of these solutions rather than solving the differential equation itself. This can be referred to at a later time. So, what are the solutions for the harmonic oscillator? First of all, there are an infinity of solutions. H psi n of x is equal to E n psi n of x, and the formula for E n turns out to be, when you solve the Schrodinger equation, E n is h bar omega times n plus a half, and n is the quantum number which can take values 0, 1, 2 to infinity. N is the oscillator quantum number. And for each value of n, there is a psi n. There is a wave function, a psi n. The general formula for psi n, when you do the mathematics, is given by a normalization constant which also depends on this quantum number n, and an exponential of minus alpha x square by 2 times the Hermite polynomials h n root alpha x. Okay. These are the solutions, or in whatever we have described so far, these are also known as the eigenfunctions of the harmonic oscillator, Hamiltonian. The eigenvalues are En. Go back and look at the constants alpha and lambda. Alpha square is km by h bar square. Alpha square is km by h bar square. Okay. K is the force constant, which is mass t to the minus 2 multiplied by mass m, and h bar is mass length square t to the minus 1, but it is a square. So, what you have is 1 by L to the power 4. Therefore, alpha square has the unit length raised to minus 4, or alpha has the dimension, I mean alpha square has the dimension of length to the minus 4, and alpha has the dimension of L to the minus 2. That should make sense because x is a position, and therefore it is also the length from the equilibrium, a distance from the equilibrium. Therefore you see that alpha x square is dimensionless. Otherwise e to the minus alpha x square by 2 does not make sense. Okay. So the constants have been chosen to get some of these physical parameters clear, and the Hermite polynomial, which is a function of position, is multiplied by square root of alpha, and you can see that square root of alpha is length inverse. Okay. Length inverse, therefore square root of alpha x is also dimensionless, so that you can add various powers. The Hermite polynomials are solutions of what is known as the Hermite equation, which I wrote down earlier, and the Hermite polynomials are defined for various values of, say, let me write h and y, if I put the argument as y instead of root alpha x. Okay. Y is root alpha x in this case. If I write h and y and n equal to 0, 1, 2, 3, etc., then the results are already known, namely h0 of y is 1, h1 of y is 2y, h2 of y is 4y square minus 2, h3 of y is equal to 8y cube minus 12y, and so on. Okay. So if you write this in terms of root alpha x, h naught root alpha x is 1, h1 is 2 root alpha x, h2 is 4 alpha x square minus 2, and h3 is 8 root alpha alpha root alpha, that is, it's alpha to the 3 by 2 x cube minus 12 root alpha x, and so on. Okay. There are relations that the polynomial satisfy between hn, hn plus 1 and hn minus 1. There is a relation called recurrence relation. Stop for a minute. The recurrence relation between these is also known in mathematics. It is hn plus 1 of y minus 2y hn of y plus 2n n minus 1 of y is equal to 0. What this tells you is to obtain harmonic oscillators for higher values, I mean larger values of n from the harmonic oscillator, the Hermite polynomials for smaller values. For example, h0 and h1, if you know, then you can calculate h2 of y minus 2y h1 of y plus 2, since n is 1, this is 2, h0 of y, that is equal to 0, and this is 1, and h1 of y is known as to us as 2y. Therefore you see h2 of y is 4y squared minus 2, which is what I had written down earlier. Okay, see that. So if we knew h0 and h1 from mathematics and also from the recurrence relation, if we know the recurrence relation, then in principle we can calculate any Hermite polynomial Hn from the previous 2 Hermite polynomials. And so one exercise would be to show that H3 of y is equal to 8y cube minus 12y, and so on. So one can reproduce these tables, and let me just show you from one of the lectures that I have had earlier. One can see the table here for various values of the Hermite polynomials. In this table, of course, y and x have been interchanged. You can see that h naught of x, and one can go on and calculate h naught, h1, h2, and what you see here is up to h8. One thing that should be noted is that the even numbered polynomials 0, 2, 4, 6, 8 are all even functions of x. h0 of x is 1, h2 of x is 4x squared minus 2, which does not change if x is negative or positive, that is minus x or plus x. h4 of x is again is x raised to 4x squared, therefore it is an even function of x. h6 of x is even. Therefore the Hermite polynomials also give us a series of functions which are odd or even depending on whether the quantum number associated with the harmonic oscillator problem is odd or even. This is something that we have to remember when we do some of the computations regarding probabilities and average values using harmonic oscillator eigenfunctions. So let me summarize this with the only other thing that I have not yet mentioned, namely if we write psi n of x as a normalization constant n and an exponential e to the minus alpha x square by 2 multiplied by the Hermite polynomial Hn of root alpha x. The one more unknown quantity that we have is the normalization constant n. And of course n is such that the integral psi n star, which in this case is the same as psi n of x, psi n x dx, between the limits minus infinity to plus infinity, because the harmonic oscillator position coordinate can go the negative direction as well as in the positive direction, and if we take this theoretical limit that the x can go all the way to minus infinity and to plus infinity, then the normalization constant requires this condition, namely can be obtained from this condition, namely psi star n of x, psi n of x dx is 1, which for n equal to 0, for example, if you want to know what the n0 square is, that is obtained as follows, namely n0 square integral e to the minus alpha x square dx between minus infinity to plus infinity is 1, because the Hermite polynomial for n equal to 0 is 1, and this is a standard integral. Its value is known. This integral is root pi over alpha. Therefore the harmonic oscillator normalization constant n0 is alpha over pi to 1 by 4. Okay. Thus psi 0, what is called the ground state wave function or the lowest energy solution, E0 is h bar omega by 2, because n plus a half will give you only half, n is 0. E0 is h bar by omega by 2, and psi 0 of x is alpha by pi to 1 by 4 e to the minus alpha x square by 2. In a similar fashion, one can calculate any n by having the normalization constant evaluated using these types of integrals, e to the minus alpha x square, x raised to 2n minus infinity to plus infinity dx. If we know the value of this integral for all values n equal to 0, 1, 2, 3, etc., then it is possible for you to calculate the normalization constant n. In some of the problems and quizzes that follow this lecture, I would suggest that you calculate these constants for the first excited state or the second energy state like E1, E2, E3, etc. You can easily calculate this using simple integral formulas, and this integral is known from integral tables. Okay? You can also calculate this using elementary integration. So, the solutions therefore H psi n is equal to E n psi n are given as h bar omega n plus a half for the E and the psi n as exponential minus alpha x square by 2 h n of root alpha x. In the next part, we will see what these things mean in terms of pictorial representations and also what the probabilities and an important concept known as the 0 point energy. Thank you.